Here we are. We're going to go over this first warm up here today, the first problem of the day. Suppose you have an investment which can be modeled by that equation there. It's an exponential function because we have the variable in the exponent. Good morning, Maddie and Kai. We're going to identify the initial value first. Well, as long as, and this is necessary, as long as k is 0. So here we do have a k value of 0. But that has to be true for this to be the case. And in investments and loans and things, that usually will be the case. This is our initial value right here. Actually, I'm going to use a different color on that. So our initial value shows up as A. So that's the $1,250. And this part is where we find the growth factor. But it's important to remember that when you're talking about an investment, we usually have something that looks like this. Y equals the initial value times 1 plus or minus the percent, which is the growth factor. So if you have a exponential growth, then this is addition. If you have exponential decay, then it's subtraction, and then it's raised to the x power. So we have to kind of undo the 1 minus, or the 1.0825. We have to subtract 1, which leaves 0.0825, which is, when we move that decimal over 2 places, 8.25%. And so calculating the value after 10 years, that's just going to be y is equal to 1250 times 1.0825 to the 10th power, not the x power. And I'll bring up my calculator and you guys can verify that I'm getting it right. So this is 1250 times 1.0825 to the 10th power. And so it's $2,761.78. So this is approximately, or it's actually equal to, because when we're talking about dollars, we can't have thousandths, we just have pennies. So $2,761.78. Are there any questions on this warm up? So the compound interest formula, we can see it there. The P there is the principal amount. So this is the initial investment or the principal. The percent is just the percent of the rate that you're the annual rate. So we'll put this as the annual percentage rate. And so the question then, T is time, that's the number of years. So let me do that. T, that is the number of years. Can anyone tell me why we have this 1 here? What does that represent? But one way of thinking about it is we have to do this the exponent here on the parentheses, but and we don't just drop it in here like that. So, but we also have to distribute this p. And when we distribute that p, that 1 represents 100% of the principal. So it's saying, listen, we have to multiply the principal by 100%, and this is going to be the percent that we're adding on. So why does the letter N in the formula show up twice? Can anyone tell me why it shows up here the first time? The percent divided by N represents the percentage calculated each time period. And that can be a month, could be a day, could be a minute, could be anything. So the time period is the N. So if we take the year, 365 days, and so the year, if we divide it by 365 here, then our time period is days. And then the N times T, well, if we didn't multiply it by N, if we just had the T, then it would change the way this shows up. So we have to have the number of time periods times the number of years. So it would really mess things up. And here, let's just have a quick look at this. I'm going to bring the calculator over, and so if, for instance, we had a $1,000 investment and we multiplied that by, 1 plus, and alpha y equals will give me a fraction. We're going to do a 15% interest rate, so I need to do 0.15. And we're going to calculate it monthly. So we're dividing by 12. And then we're going to raise that just to 1 year. And when we do it to 1 year, then that's what we get. But if we change, if we change this to 1 times 12, which is the way it shows up in there. So notice how much difference it makes here. That's quite a lot of difference. And if we continue to look at this, so if we take this and we do it by 2 years instead of 1, that's what we get. And if we change this one to 2 years, so the difference there is really getting to be big. So we're not it doesn't take into account the number of times per year that we're doing the multiplication. Takes into account the number of periods. So we have to have it twice there. All right. So in the Desmos, you saw how to change the number of compounds in a year. So you could do it, you could compound once. So in this case, the n was 1, that's just yearly. If n is 1, it doesn't actually show up there. If you want to compound 12 times a year, so monthly, then this becomes 12. If you want to compound daily, this becomes 365. And so you can continue to compound in all kinds of different ways. Was an investment or loan worth more if interest is compounded annually or monthly, and why? Anybody out there willing to go out on a limb and give me their ideas here? If you want to make more money, should you get an investment account if they're both have the same interest rate, compounded annually or monthly? Well, it's annually. So what that means is that the principal is rolled over and calculated the multiplication more often. So the principal, well, let's say this, uh, the interest is rolled into the principal more often. So you get more money that way. All right. So I'm going to give you just a minute to use the Desmos graphing calculator and figure this out. Okay, so here's what you're going to put in the Desmos graphing calculator. It's a $1 loan, and it's 100% interest. So it's the 1 plus, and this 100% interest shows up right here. That's 1 over, and the n is going to be whichever of these you're looking at. So annually, n would be 1. And then this is going to be n times t. And I also want to show that this $1 loan, that is this one right there. All right, so I'm gonna give you just a couple minutes to do this with the Desmos calculator, and I can put the link to the Desmos calculator in the chat. All right, so you've had a chance to look at that, and we're writing down the amounts of each of these possible loans. So using my calculator here and giving the estimates. So now I'm going to look at weekly. So instead of dividing by 12, I have to divide by 52 and then raise to the power of 52. And that comes out to be approximately 2.693. Now I'm going to figure out the amount if it's daily. So 365 is the n value in our equation. T is still 1. So that's 2.715. And hourly. So I had to do 24 hours times 365 days to get the 8,760. And so I'm going to go in and change that. And it's 2.718. Whoops. 2.718. Now my question is for you, and if someone would be willing to share their thoughts, I'd love to hear them. What do you notice about the difference in dollars as we increase the number of compounds? Anyone notice anything interesting there? Well, when we went from yearly, annually to monthly, we had an increase of about 61 cents. Then when we went from monthly to weekly, we had an increase of about 8 cents. And then when we went from weekly to daily, we had an increase of about 2 to 3 cents, just about 2. And then when we went from daily to hourly, we didn't even increase a half of a cent. And Annika says it's increasing by smaller intervals. That's right. And that's really important to notice. And this is something that Jacob Bernoulli discovered in 1683. So he was doing this same thing. He was looking at this same pattern here. And what he found was if you increase more and more and more, something very, very big happens. So check this out. So I'm going to go up here and I'm going to change this to, I changed it to 10 nines. I don't even know what that number is offhand. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Any ideas out there what's going to happen? Well, let's see. Oh my goodness, look how close it is. It is now only increasing by about 0.00016. Wow, that is not much. And this is a big deal. There is this number, Bernoulli said, E. And E is the number that we are getting closer and closer to. So if we made this value even bigger, we would be closer to E. All right. So he came up with this idea of compounding continuously, not by the half second, not by the quarter second, not by the eighth of a second, but if we could constantly, every even smaller than whatever a millisecond is, always compounding, we would get a number approximately 2.718, and that is E. So it's just an incredible idea that there's this number and the decimal goes on and on and on, never repeating. Okay. So now I'm going to have you guys explore some exponent properties. We only have about 5 minutes left to do this. So here's the deal. I'm sorry that you don't have a lot of time to do this. I wish there was more. I need you to practice this. So there it is. And there's also this exit ticket that I would like you to do after you do the practice. So you don't have to do it right now. I'm going to end the recording here.